This is an Innovation Connect project, as Ryan pointed out. It started off the first phase of the Innovation Connect started over a year ago and finished, and we're now into the second phase of the Innovation Connect. It was primarily designed really to map the mineral zoning patterns around these turbidite hosted gold deposit, or one of them in particular, the Wattle Gully deposit in the central Victorian Goldfields. And we used some different technologies and that hadn't been sort of applied to this part of the world before to sort of try and sort of see if we could find some more cryptic, less well understood zonation patterns, and then think about strategies on how we could use those zonation patterns in exploration throughout the district. I'd certainly like to just acknowledge the sort of the team that I work with. It's John Walsh, Katie Woodall, Tina Sheldon, and Tobias. More recently, Tobias has sort of been taking a lead on particularly doing a lot of the mineral analysis using the probe for some of the microchemistry. So it's sort of, he's really leading the second part of this, but most of this talk's really about the first phase. We'll get to the end of it. When we get to the end, I'll talk a little bit about some of the applications and the findings of the preliminary findings of the white mica sort of work. I'd like to sort of also acknowledge the Innovation Connect sort of initiative, which supports and sort of definitely sort of adds funding so that we can go out and do apply new sort of technologies to exploration in different terrains where we hadn't worked before. So this is a talk outline, just the detailed mineral zoning pattern around Wattle Gully deposit in the central Victorian Goldfield. It's really was used like an automated TIMA mineral mapping, so it gets a very comprehensive database as well as the textual understanding of the rocks, and therefore we can get greater sort of certainty around the types of minerals that occur around the deposit. I'm then, toward the back end of this talk, I'm going to present some more recent stuff we've been doing with LIBS, which is a it's similar, it scans rocks, but it's very sensitive, and it gives some really unique insights into some of the elements. It's very sensitive, so you can see zoning within particular phases that you might not see using other techniques. And then at the end, talk about some of the district applications and some of the preliminary results where we've done a lot of coverage, 5 to 10 kilometres of coverage over areas that are less well understood, and seeing if we can detect some of the zoning patterns that we've come to understand from our work around Wattle Gully and another sort of prospect in that area. So this is the sort of the strategy, the cartoon sort of illustrating, you know, possible exploration strategies, and one that I'll sort of keep touching on here because of what we found through phase one, and that's certainly looking at the white micas. Chemistry was something that was very useful. Dennis Arns, he did some hyperspectral work through the central Victorian Goldfields, and certainly with the hyperspectral also noted back in 2016 that there were these very interesting shifts in the hyperspectral, which showed more aluminum rich, if you like, muscovite around sort of some of the lodes, and more background distal pangitic. So we're going to try and leverage some of that information, but also look at some of the other zonings, like such as arsenides and that, and also some of the different carbonate minerals. In this map, it's a sort of, as you can see, there's some soil sampling there, which is designed to sort of go across 100-metre space and 200-metre space lines. And maybe if you're doing this is just a cartoon, but you might sort of pick up changes in your white mica chemistry, which might signal that you may be close to something, and that way another sort of tool in your kit, if you like, to sort of try and work out where you are relative to a possible lode that you may not see because it might be covered, it might be at depth. a lot of that understanding that we use where we might use in exploration, in soil sampling, it should come from our understanding of the deposits. So what are the zoning patterns? So as I pointed out, these muscovite zones, but also these little brown lines would be the carbonates. And then there's some different arsenide minerals like cobaltite. So if you're going across through the saprolite and you're doing your 100-metre spacing, and then you hit a muscovite zone, well, you might sort of increase your sampling around those areas. And then if you've got greater sort of certainty around those, you might put an RC hole in or something, and then a diamond. So it's sort of, but we need to understand that zoning pattern so that we can apply it back to those exploration strategies, and that's really what this is about. So I'm going to present some of the tools that we use through this project, such as portable XRF, but there's also Ryan's work with the ultrafine, or there's multi-elements, and these are really useful for defining the rock types and element anomalies. I'll present some TIMA work today, and this is really useful for the detailed mineralogy of samples and the rock texture, so we understand the timing of different alteration events. And I'll get into the libs, so the detailed element maps, rock textures, some of the lighter elements that we might not see, such as lithium and whatnot, that we might not see through other techniques. And also we'll touch at the back end of this on some of the probe work, which has really given us accurate, reliable sort of gold standard, if you like, mineral chemistry. Okay, so the TIMA, I'll start off with some of the TIMA work. For those who haven't sort of had any exposure to it, it's similar to a QEM scan. It's basically, it rasters across at, down to half a micron, picks up a spectra, and we've got a library, and that library determines what mineral it's likely to be based off the chemistry, and it gives full quantified mineralogy down to sort of almost ppm sort of roughly levels, and those can go into Excel spreadsheets, and then they can be put in, once you've got quantified mineralogy, you can see the textures, but you can also put those into your models and have quantified mineral in the model. It's a slow, and there's a lot of sample prep, but it does give a lot of detail that you don't otherwise get. So this is the area, central Victorian Goldfields. It's in the Bendigo domain around Castlemaine, and here's a bit more of here's the city of Castlemaine, just to the southeast, Wattle Gully, and there's also Chewton, and it's chevron folded sort of turbidite sequence. So the blue there being more mudstones, and the yellows and that being more sandstones. And this is some of the work. These are the holes that we worked on across this. So the yellow there, this is some of the portable XRF where we've used it to define the rock type, and that being a sandy unit, where the blue being the mudstone. So we're getting, from the portable XRF work, getting a good understanding of the rock type, and then understanding the mineralogy relative to the rock type. These are some of the chevron folding that we will see. These are the gold assays, so the Wattle Gully fault zone with gold values. There's also Chewton over here, which we did a bit of work on. One of the things that we noticed when we do look at the texture of the rock and also the portable XRF data is that there's been a lot of fluid pressure in parts of these rocks, and we see things like changes, if you like, or increases in volume. There's a lot of sort of quartz grains, and then we start to see carbonate sort of established between the quartz grains. So these quartz grains start to separate, which we put down to a bit of a volume increase. And it's quite interesting where those volume increases occur. In particular, where we do see there's not a lot of carbonate alteration in the hanging wall, but as we get around, here's the gold here, there's notable alteration like arsenic, but also iron-rich carbonates, and around them we will see a lot of sort of calcite, and that calcite will, in sandy units, if you like, will sort of fill in the spaces between the quartz grain. It doesn't look like a replacement reaction; it just looks like the the volume of the rock had increased in those areas, and that's what the chemistry sort of suggests too. And what's interesting is they sort of envelope, if you like, they occur around the margins of where a lot of the very interesting alterations, so that the more siderite, arsenic occurs. These zones, which are wider than the gold, have been picked up by Dennis Hahn with the hyperspectral high logger, notable sort of iron-rich carbonate zones. This is at Chewton, and also changes, if you like. So you've got fangitic, and then you go into more muscovite, where you start to see the gold. So one of the things that we do, like I said, we need to establish before we sort of try to sort of apply our zoning patterns and that to the rock just based off quantified mineralogy, is obviously understand the rock type and have a method that sort of appreciates the type of rock you're dealing with. So with the portable XRF, we're able to differentiate sandstones from mudstones, and from there, and then put them again on the section. And from there, we could also look at the abundance of minerals in different rock types. So if you just look at muscovite values or fangite values in your rock, it's not really going to be that useful if you don't know what rock type you're in. And so as we can see, the mudstones have a lot more white mica in them relative to the sandstone. So we need to really appreciate that. And when we're handling the data, we need to acknowledge the rock type we're in, and with respect to the mineral zoning. Other things like albite are typically, this would be the more sandy units, so you start to see more albite in the sandy units. Where other things like iron-rich carbonates, they're a bit more they're broader across both the mudstones and the sandstones. So the sandstones sit down here, and the mudstones are up in here. One of the things that from the TIMA work, when we looked at the analysis of muscovite versus fangite, is that those samples which were in the hanging wall, away from mineralization, tended to have relatively low amounts of muscovite relative to their fangite. So as you got closer to the lode, essentially the micas became more aluminum rich, and that didn't matter which rock type you're in. So even if these yellow ones here are sandstones, so we start to see the sandstones, even though they've got small amounts of white mica in them, that white mica is more aluminum rich than what it would be if it was in the hanging wall we found from the section we worked on. And so what we're seeing here is that the aluminum sort of iron and silicon substitution into the white mica. So as you start off, you're more in a fangite, but then as you get closer to alteration, essentially those white micas are becoming more aluminum rich. And it doesn't matter what rock type you're in, and that's really important. Here the sandy unit, so it's a lot of quartz, so there's a bit of carbonate, which is blue, and the light blue there is albite. And we can see if we're getting close, there's little bits of muscovite in the space. So that's even though that's a small amount of muscovite, we do see changes in the sandstone if we're near the lode versus if we're away from it. That composition of that white mica is changing, even though it's trace amounts of it or small amounts of white mica. And that's really important. So it's a chemistry of the white mica, not the abundance of the white mica, that is really, really critical. And here we have ratioed, if you like, so the aluminum white mica versus the fangite. If we're in around the lode, there's about 170 meters where that ratio is much higher than if you go up into the hanging wall. And that corresponds with areas where we get more iron-rich carbonates and also arsenic. It's quite a subtle difference, and that's why later on you'll see we went to probe work. But also, this is where I want to bring in some of the lib stuff, because the lib is very sensitive around some of these elements and can really distinguish. But if we do, this is some spot analysis on the samples. So we took a mudstone which had quite a bit of white mica, from the ore zone, which is in the purple. And we see relatively lower amounts of, definitely lower amounts of iron. There is certainly an overlap with the magnesium, whereas those that are sort of more distal, we start to see increased amounts of both iron and on average magnesium, but there is an overlap. So, and if we put that onto the zoning, we can see that these purple zones here are where essentially that muscovite to fangite ratio is much higher. It lights up the ore zones quite well. It's not as well developed in as Chewton, but Wattle Gully is a far better deposit. We see that this is just portable XR arsenic, portable XRF arsenic, and we see those arsenic values there. But there is some little traces of mineralization in the hanging wall. But a lot of the arsenic sort of from the portable XRF also sits over those sort of those muscovite rich domains. And there's not a lot of arsenopyrite. Most of the arsenic is in cobaltite, which is a cobalt arsenic sulfide mineral, and that's quite a broad halo around the system. We can actually have a look from the textures. This is a TIMA map. So there, the blue there is calcite. This is cross-cutting a sandstone with some pyrite. There's trace amounts of essentially cobaltite in some of these samples, and you can sort of see the dot. This is just an element map, so of the one before, where there is actually increased. Each one of those pixels is analysis of arsenic. So those carbonate blebs have essentially arsenide in them. And we can also see through some of the veins, there's cobaltite sitting with a pyrite in quartz vein. There might be some calcite in some of those veins too. And we think they occur about the same time as mineralization. One of the other key features is the siderite, and it's these little sort of stringers, if you like, of siderite, cross-cut in this case, mudstone. And as you can see, around the Wattle Gully lode, we do see a lot of that's where most of the siderite sort of sits. It's another very, very good zoning pattern there. So we can sort of see the siderite. We can see some calcite that sort of sits around it. There's also little bits of kaolinite. So the fluids, in a sense, maybe becoming, in parts of these systems, might be a little bit acid, and they sit with some very interesting alteration assemblages, which we think also occur around about the same time as gold. So here's some of the kaolinite, which, the system from a trying to understand the fluids. If we went from a more calcite stable environment out into more siderite, and then we went into sort of the kaolinite, we might be sort of going into more of an acid, and that might also correspond with some of the changes in the white mica chemistry. So yeah, and one of the reasons that's sort of interested in the kaolinite is that there are some deposits or prospects in the area which have a lot of kaolinite alteration around them, and that kaolinite alteration looks like it could be related to the gold mineralization. Yeah. So just a bit of a cartoon, a cross section, just to sort of summarize some of the zoning patterns there. So we have this muscovite sort of, and these siderite sort of veinlets sort of cross-cutting, and then there's this outermost cobaltite zone. And the importance of this is what would sort of survive up in through the cover, and essentially the white micas would. And so we're going to put a little bit more effort into sort of understanding how to map sort of the white mica chemistry, and perhaps use that as a bit of an exploration tool. And this brings us to sort of some of the LIBS work. So the later induced breakdown. This is a really sort of rapid, it's very sensitive sort of method, and it sort of creates very, very nice sort of element maps for particular elements, and the speed of it is something that sort of puts it in a sort of an area of its own. And this is, I'm just going to show a bit of a video here, just the scanning across. To do a 1.5 centimetre square, you know, we're up to a couple of minutes. This laser just goes across and creates essentially a plasma plume. And from each one of those sort of pulses and that, it creates a spectra. And if I, whoops, go to the next slide. If we create a sort of these element maps, from those element maps we can filter certain minerals. In this case here, we've filtered based off biotite, so we can understand the chemistry. We can go through and just filter out those spectra and then start to look at the chemistry of that particular mineral in the sample. And just to sort of emphasize the quality of the spectra and also the sensitivity, these are two sort of spectra from one of those pixels that would go across a sample. There's a 300 by 300 meter grid, certainly about 90,000 spectra, if you like, for a map. And this is one of those spectra, and you can see peaks such as the magnesium and certainly potassium. But also, what I want to point to is the difference in some of the lithium peaks. So here, this would be muscovite from the lode zone, which essentially has a low lithium count compared to the lithium from the fangite, which would occur in a mudstone in the hanging wall. We can also see, so these are more fangitic, but you can see that, I mean, this is over 40,000 counts of magnesium in the fangite from the hanging wall, versus if we were essentially, or in the lode zone, that mudstone, those white micas, which are more aluminum rich, we can see a much lower magnesium peak. So it's really, really sensitive, and that sensitivity is quite valuable for trying to sort of understand these more subtle shifts in the chemistry of the white mica as you get close to ore zones. So this is a map. This is our TIMA map of a mudstone. So the pink being muscovite, and there's grey in there with quartz. There's also pyrite. What I've done here is I've gone through and just filtered from the live spectra the pixels that are white mica, that are essentially either fangite or muscovite. And as you can see, this is for iron. The iron counts are around 6,000 for a sample, a mudstone that is 400 metres away from the lode in the hanging wall. If we take the same mudstone, which is closer to the lode, we can see that if I filter those maps for the white mica, we can see a much lower range of iron values for the white mica. So it's more around 5,000. And there's a lot of interesting textures that we see here. So this is where the sensitivity of those peaks actually allows us to actually see some details in the white mica in these samples. Some of it can be mixed spectra, but in many cases, when you compare a sample from the hanging wall to that in the lode, you can see the distinct differences. So this is just to put them side by side. The white mica in mudstone from the lode versus the white mica from the iron values from 400 metres from the lode. And we can have a look at other things like the magnesium shows a very similar story. So that's becoming obviously that fangite to muscovite, so it's very, very sensitive. And another one that's very interesting are the lithium peaks. So we can start to see here that lithium peak when we're in the hanging wall is around 12,000 versus when we're near the lode, it's more likely around 8,000 for the white mica. So it looks like from these maps that the white micas in the mudstone are essentially losing lithium, they're losing iron, and they're losing magnesium. And this is all the pixels from a particular map. So they're the counts of potassium on the y-axis. This is from the mudstone in the hanging wall. So we get about 56,000 counts of potassium for and we can have a look at that population of white mica, and the lithium counts are around 12,000. Whereas if we took that population from the mudstone around the lode, it's around about 7,500 lithium count for about the same Italian value. So though I think those white micas, which are becoming more aluminum rich, again, this is just more evidence just to show that they're also likely losing lithium. And so this is a bit of a summary, if you like, of one of the reactions, particularly focused on the white mica. We have a fangite precursor mudstone, and we put in CO2-rich fluids, and essentially that strips out the iron and the magnesium. Maybe that iron and magnesium goes into the carbonate. We're also losing silicon, but there's aluminum. You have to have an aluminum increase, if you like, whether it's a volume change. So there's essentially these elements, whether we're forming quartz and siderite in these veins, which seems likely, because that's what we see from some of the textures. That may be we're a home, if you like, for those elements when you cause this reaction. And the lithium, well, we can't sort of track where the lithium's gone, but it certainly looks like it's going out of those phases. So back to, okay, we can sort of map the white micas, which we think are really very, very useful. I think the LIBS really does emphasize the sensitivity of the LIBS, if you like, really sort of highlights some of the key changes in the white mica chemistry as you get closer to the lode. And we can sort of leverage that information, if you like, because if this is from Ravi Anand, essentially the white micas will survive up through the regolith, where the carbonates or the arsenides, the primary arsenides may not, will not. So this sort of gives us a tool to go off and explore into the saprolite. And we know from some of the work that we've done before, looking at this as sort of air core samples, so the chip samples, where we see in a relatively fresh rock, we can see the white mica, K feldspar, plagioclase quartz. As those rocks become weathered, we start to lose the feldspar. The quartz survives, but you still get these books of the white mica. So that sort of backs up a lot of the work that Ravi's done with his profile, showing that white mica it survives up into the regolith and it can be used. And so this is sort of where we got to, if you like, with the second phase, doing these sampling campaigns of traverses across particular areas, going through, just digging down, and then getting soil samples or regolith, and then separating the white mica out of it. And this is some of the preliminary results. So this is that's 1 kilometre. I think it's about 6 kilometres or so, and it's about 5 kilometres. This is the South Muckleford Area, and this is all these data points are essentially samples where we've separated the white mica, and then we've done probe analysis on it. So this is a lot of the stuff that Tobias has done with Katie and Tina. So if we have a look at some of the results of that, so the red there essentially they're your essentially the muscovites, and or the bigger the bubble, essentially the more the lower the amount of iron in those white micas. And you can see that they've had historical mining, historical working around the blowhole. There's also red, white, and blue. And I showed at the beginning some of the alteration around Dunn's Reef. We can see that there are these zones, particularly around the blowhole, where we start to see more aluminum-rich white micas from those traverses. So that seems to sort of flag out some of these areas as being aluminum-rich white micas, where these areas out here, it would seem that they are more fangitic, and there's not many gradients in those areas too. So I think you could use these sort of maps in combination with multi-elements maps and stuff to look at arsenic and gold, but sort of build up sort of a detailed sort of footprint on where your aluminum-rich white micas are going. It's also important to point out that the white mica chemistry, there's been quite a bit of work done in the yield gun. Ray Wang sort of did publish some work, I think, back in 2017, and it basically showed that if you're at, I think it was, if you're at KB, the fangite zones actually are closer to the lode, whereas some other deposits, actually it's the muscovite. So there is switching, and that can be to do with the fluid chemistry, but it's the switches that we should be paying attention to and trying to understand why those switches are there. So it also, the work done with the libs sort of opens up possibilities to go off and actually look at some of these soil samples and have a look at the white mica chemistry in the soil samples because of the sensitivity. So whether we got pressed powdered or some way press some of the regolith samples and then just scan them and then start to filter the white micas from it. This may be another way to sort of detect, if you like, the low lithium white micas and sort of add value or information to those maps. And it's a quicker, potentially cheaper way with hopefully less sample preparation to build these maps more rapidly going forward. So the conclusions is that yes, the muscovite fangite zoning, you know, first highlighted by Dennis Ahn, certainly it increases the alteration footprint. If you saw at Wattle Gully, that footprint is about 170 metres downhole in width, and so that's a significant increase on that. And that corresponds with arsenic and also the iron-rich carbonates. The muscovite to fangite zones, as we've shown, can be mapped through into the regolith, and that would certainly add value to gold assays or arsenic sort of assays that are done on the soils. And I think again the LIBS work, you know, might be a very useful way to sort of work on some of those saprolite samples to sort of gain sort of an understanding, if you like, of the detailed chemistry because of the sensitivity around some of the peaks. And that's it. So thank you very much.
Thank you, Adam. And I'd also just like to thank Kalamazoo Resources and the Innovation Connections project that makes these types of research engagements with SMEs in particular so valuable and actually work for us. So that's the end of our presentation. We will now take any questions. If anyone has them, they can pop them in the chat function or come off mute and ask them to Adam directly.